Talk about how to analyze the data, how to store the data, and how to do other things with the data, but often you just want to look at the data and get some sense out of it and visualize it to begin to understand it. And Jeff here has made a career out of trying to visualize data and using all manner of interesting approaches, some of which I think we'll hear about today. Great, Jeff. He's an assistant professor at Stanford University, I believe.
That's right. Yep. So I teach in the computer science department at Stanford University. Thanks for the introduction. So actually, I should admit, I'm a newcomer to medicine. Still getting a grapple on medical data and some of the interesting problems the field faces. But even with that limited background, I have to say, I already have a deep appreciation, particularly historically. I think medicine and medical researchers are at the forefront of using visual methods to gain new insights. And so this includes various techniques such as staining. So this is an instance of gram staining. We use a chemical treatment to be able to classify different types of bacteria. And my personal favorite is Golgi's method of staining, which many of you are probably familiar with as it was used by Santiago Ramon y Cajal when he really laid the foundations of modern neuroscience. And one of the things that amazed me was this particular form of staining actually has interesting analogs to how we do information visualization today. Part of the problem was like the bundles of neurons that he was exploring were just too complicated. It was too hard to follow individual strains. But the particular chemical properties of this stain allowed it to follow along neuronal paths, these transmissions, so you actually see which axons connected to which dendrites, etc. Thus, by filtering out some of the other data that was there, revealing interesting patterns into neural structure, which really did lay the groundwork for much of neuroscience to come. And perhaps also interestingly, and maybe a lesson we might learn from, was this quote I like from Santiago Ramon y Cajal, who said, "I express the surprise which I experienced upon seeing with my own eyes the wonderful revelatory powers of the chrome-Sybil reaction and the absence of any excitement in the scientific world aroused by its discovery." And so sometimes even when we have methods at hand, we don't necessarily realize their value. And so fortunately, we do have those explorers who make those important connections. So I think something all we want to keep in mind, especially I think as it's accelerated by the data we will hopefully have ever more accessible to us as researchers. Of course, there are many other visual methods, continuing physical process such as the X-ray here being used to find a tumor, which I'm sure you can spot. And also moving on to digital methods. So, fMRI, certainly a physical process, but then later digitized. And what you're seeing here is not just visualization of raw data, but really the output of a series of statistical processes that have been applied to the collected data. And then, of course, we can move along to some of the things we've been discussing over the past 2 days. So the various physiological data we might collect to help improve diagnosis and, in the end, improve outcome. And one thing that struck me in the 2 days I've been here is that there seems to be one single central metaphor driving much of the discussion, and that is the patient is data. And I think it's worth that we just ponder that for a moment. I think it's a very important and very powerful perspective, but it's certainly not the only one. I think it's, perhaps even just impolite to suggest that, patients are people too. And that has interesting implications. Certainly that people themselves can help collect data. For example, it might not be how do I improve outcome when someone's in the hospital, but how do I prevent people from having to go there in the first place? And that might include rich data we collect, maybe self-report, collecting these devices that we carry around with us all the time, and also access to really interesting activities that people are doing online. You may be familiar with Google Flu Trends. That's one example in which data, the actions of a number of uncoordinating individuals might provide some interest and some insight into public health policy. So we'll revisit some of these topics and some of these different types of data throughout the rest of my talk. And so by name, I'm a visualization researcher. I lead a visualization group. And indeed, much of the research we do is exploring how can we create new visual representations of data that aid exploration and increase our ability to, for example, generate valuable hypotheses. We also study empirically some of the perceptual processes involved to try and decide which visualization techniques work better than others. But really to refer to ourselves as visualization researchers might actually do us a disservice because what we're really interested in doing is supporting data analysis. And so the problems that we contend with are not just how do we take a data set that's been handed down from some unknown source and turn it into a picture, but rather how do we support the various cycles and stages that we deal with as we make sense of data. How do we acquire data, assess its value, clean it, integrate data sets together, of course visualize it, conduct analyses, and then present and disseminate information. And it might be convenient to think, well, with the right tool stack, we can just start at the beginning and work our way through, and at the end of the day, produce insights. I think any of you who have done any real data analysis know that this picture is a complete fallacy. And data analysis really looks something much more like this, where the outputs of one stage end up, surface our mistakes, whether it's mistaken assumptions or errors with our data, or the need to revisit our model, et cetera. And what this implicates us in is that there is a very interesting iterative process that we have to engage in, and we have to be able to deal with interaction techniques that allow us to manage this process. While it would be great to be able to automate this as much as we could if we could do so reliably, unfortunately that's not the case today. And so we have to consider how can we also design the tools that will enable us to be more effective data analysts. And so what I'd like to do with the remainder of the talk is just walk through a couple of examples that come from this data lifecycle to get an insight into how we might create better tools for analyzing data, in particular medical data. So I'd like to start with a problem that's already been mentioned multiple times throughout the conference, which is issues in data cleaning. Multiple people noted that oftentimes data arrives in inconvenient format, or even if suitably convenient, one wants to transform it anyway for one's own purposes. And typically this is a very tedious process, whether it's manual manipulation in spreadsheet tools, which simply doesn't scale, or requires programming knowledge as we write scripts, for example, to transform data from one form to the other. Wouldn't it be nice if we could accelerate that loop, which, if you interview data analysis, as we have, find out is a serious detriment to their analyst process and takes up quite a deal of their time. So here's an example of a data set. Unfortunately, I didn't have a medical example at hand, but this one comes from catalogandData.gov. This is from the Bureau of Justice Statistics, and this shows housing data for different states in the U.S. Relatively clean data, relatively well organized, but if you try and import this into any standard data tool, it will completely break. It doesn't follow any known format, so it might seem a trivial thing to do this, but now you have to break out Python or whatever your favorite scripting program is, and then wrangle this data into a shape that's useful. And unfortunately, while this is a very common practice, at least within the visualization community, these issues of data quality and cleaning and transformation are something of an elephant in the room, where we kind of assume we're being handed nice data that's just waiting for the insights to be discovered within it, when of course we know this is hardly the case. So let's look at one tool that we've developed to try and help with this process. This is a system called Data Wrangler. So let me just pull up the demo here. So in this case, I'll take a simplified version of that housing data I showed you earlier, and we'll plug it into the tool. And in this case, it can make a couple decisions for us. It can see that we can break the data on new lines and separate it on commas, because that's pretty common. In this case, a comma-separated value format. And then it gives us a tabular output along with some quality indicators. And now we like to transform this data, say, so we might be able to load it into a database, visualization tool, or build statistical models in R, whatever it is you'd like to do next. So now we have to take a couple steps to clean this data up. So the first thing we might do is say, let's get rid of these empty rows. They don't seem to be helping us. So I can click that. And basically I've communicated to the system that I intend to do something with that row. And so naturally it says, well, what might you do with the row? Well, it's empty, so you could delete that row. But I can also, given that input, try and generalize that idea to see what other operations might be available. And so what you're seeing on the left here is a number of suggestions of the types of operations you might perform on your data, coupled on the right with a visualization of what that operation does. So in this case, for example, I can click the down arrow and go to the generalized selection of deleting all the rows, hit enter, and I've moved along in my data cleaning process. Well, now we see that each state name is contained in its own row. We'd like to associate the state name with every record in the data set. So I might indicate that intention here by selecting the text Alabama. And then it makes a number of different suggestions, the simplest just being by index. So what position in the string did you select? But by giving it some more input, it can generalize that selection. So in this case, correctly inferring a regular expression pattern that will extract that state name from the row. So now I have my state names, but I'd like to duplicate them in the empty cells. So in this case, I actually click an indicator showing me the amount of missing data within my data set. And then I get a number of suggestions as well. And in this case, I find the desired fill. And now I'm moving along, and I might want to get rid of these extraneous rows. And I could do that, say, by deleting things with empty values in this column, or things that don't parse correctly, indicated in red in this column. But those are actually error-prone, because there may be things that are missing or don't parse that I don't want to throw away. So if I want to make a more specific operation, I can just select this substring. It makes some suggestions, and then maybe I can give it some more guidance, tell it I want to issue a delete command, and then it arrives at the desired operation. And so the point is, we can have tools that help accelerate this process of data cleaning and transformation, making this data, basically less cumbersome to work with. But the important part is the output of this process isn't the clean data. So now let's say I want to export this data for use elsewhere. Certainly I can export that data. I might want to rename the columns first, and then I can use it, whether it's in Excel, or if I want to do web-based processing, I could use JSON. But more importantly, what I've done is actually written a program. And so while I've done all these operations, I've constructed a program for cleaning this data, and I can export the code itself. And this is really important when I deal with data cleaning at scale. So for example, if I take this a small sample of my data set, I might wrangle it in these interactive tools, and then I get back a script which I can run against a MapReduce cluster and thus work with data at scale. Now we're currently doing research following on this, is that when you run those scripts, how do you deal with any of the exceptions that might result from that process? But what we're trying to do is take these interactive interfaces and couple it with the act of end-user programming, so basically writing these scripts to make working with data a little less cumbersome. So that's just one example of ways that interaction and visualization might assist within the data lifecycle. So now I want to look at a number of different examples, using visualization directly to try and make sense of data. And I'd like to start with a classic example that was developed by a statistician. So imagine I give you this data set. Now granted it's small, but it's here for an instructive purpose. And I ask you, help me make sense of this data. Are there any interesting similarities or differences that I'd like to note? Is there something interesting happening amongst these different variables or amongst these different sets? And it's certainly a good practice to eyeball raw values. Certainly, it's hard to do in its entirety, but at least gives you a sense for some of the issues of what might be happening in your data. In this case, you might notice a number of things that are maybe interesting to note. For example, the range of values, you get a sense of that. Certainly within set D, it might have jumped out to you that there's a lot of repeated values. But beyond that, it's often hard to assess maybe higher level patterns. Are these variables correlated in an interesting way? And so a perhaps naive first step to do would be compute descriptive statistics. So for example, I might look at the means and standard deviations, or if I have a reason to suspect a linear relationship, I might do a linear regression. And the reason I only have one set of values here is it turns out each of these different data sets gives the exact same result. Same mean, standard deviations, same linear regression. Now, I guess you can figure out where I'm going with this. If we instead plot the data, having chosen the right visual representation, we immediately see interesting underlying patterns that might affect our modeling decisions. For example, whether or not linear regression is a reasonable choice in the first place, let alone looking at the parameters of a Gaussian distribution, which we're assuming with the mean and standard deviation. And while this is a toy example, it illustrates a phenomenon that occurs regularly, that if you don't look at your data and assess the underlying patterns, you often make mistakes, whether it's missing erroneous values, missing values, or applying the wrong model to the data. And I think Stuart Russell also showed a number of great examples of this in the context of time series data yesterday. Another type of issue comes up is erroneous values. What you're seeing here is actually records of juvenile offenders in the state of Maryland. Age is on the x-axis, length of stay or incarceration is on the y-axis. Anyone notice anything out of kilter? Right, so you may be physically assaulted by an infant or a centenarian. Which is actually interesting. You might just say it's dirty data and throw it away, but oftentimes there's some reason to this as well. Like people don't know the age, and so they encode it intentionally using bad data. And I haven't worked directly with electronic health records, but I'm told that issues like this occur quite regularly as well. So at least as a first step and a guard to further analysis is how do we choose the right visual representations to unearth data problems before they get in our way. And these are relatively simple examples, so let's look at something a little more complicated. So here's an example of a social network. In this case, the data was pulled from Facebook using a standard visualization technique known as a node link diagram. So in this case, the circles represent people, the lines represent friendship relations between them, and the size of the circle in this case reflects the value of a betweenness centrality, which is a statistic that basically at a high level tells you how central an actor is within that social network. And we might see some patterns here that are of interest to us. We certainly see some major clusters, one large cluster in the center, and then some satellite clusters as well. But beyond that, it's quite hard to see more. And so I'm actually not very much a fan of these types of visualizations because as your data scales, you cease to see interesting patterns and substructures. So when we have to think about this, well, what's the right visual representation for getting a better initial look into our data? So one alternative to the node link diagram is what we call the matrix diagram. And so in this case, the rows and columns represent people, and each blue dot represents an edge. So the relationships are being put front and center. And to try and reveal structure within the data, we've actually done some analytics as well. In this case, we've seriated or sorted the rows and columns based on a metric that tries to put highly connected people next to each other. So in other words, if you're a friend with someone and you share lots of friends in common, you should be placed more closely together within the matrix. And there's lots of ways to optimize this, but in this case, we begin to see more of the substructure. So in this case, this big block in the center is actually that large cluster we saw in the earlier slide. And we can already begin to see some division. So for example, there's two major subclusters in here. In this case, this little satellite group gets in the way, but you can still see a lower density of edges between these two groups. And this indicates some substructure within the data that was hard to tell in the previous slide. But I'm not done, because there's something interesting going on here, which is by trying to sort the rows and columns and reveal structure, I never actually looked at the data in its raw form. And it's often quite instructive to do so. So here's what the data looks like sorted by its Facebook ID number. So basically, roughly, that's the order in which people joined Facebook. Did anyone notice something strange? Right, so this is maybe like 20% of the data, 20% of the matrix is empty. Any thoughts on why that might be? Right. So one hypothesis we could form is, well, if you're new to Facebook, you don't have any friends. At least that's not quite right. You don't have any friends who've also joined the system recently. But I think we have good grounds on rejecting that hypothesis, even just from personal experience. But it turns out that's not the case. Oh, okay. So it could be your friends are there, but you just haven't found them. Turns out most people, when they get invited, they often immediately get friended by a number of people, including recent joiners. So there might be another hypothesis we could make as to why we have this blank space. Yeah, and that's absolutely right. So it turns out the Facebook API has a 5,000 result limit on the queries, and it fails silently. And so then if you were to take the result from that query, not realizing that, run it into social networking analysis software, or even just node link diagrams or smart, sorted matrices, you might have missed that problem and have compromised your analysis as a result of that. And so this is one example of missing data that's often quite difficult to find, where it's not missing along one particular variable, and you can look at values, say, in other columns to recognize that it's missing, but rather you're missing entire records altogether that are central to your phenomenon. And so these are hard issues, and you have to be skeptical. You have to be looking for them, but through the right choice of visualization technique, this can help you get off to the right foot and avoid problems. So that's one example of using visualization for these forms of exploratory data analysis. I'd now like to share with you an example of exploratory data analysis we've been doing with some medical data. And this is actually work being done by my student, Diana McLean, at Stanford. And we're really interested not just in medical data gathered in hospitals, but also how people are dealing with health information and their own symptoms and conditions kind of out in the wild, as it were. So among the other things we've been looking at is a website called MedHelp, which is one of the largest public forums for people to form communities and discuss often chronic medical conditions. So it's a kind of a standard forum type site where users come in. They can be anonymous if they choose by their choice of handle, et cetera, and can participate in communities and discuss different issues. And we were interested in figuring out how do these communities function. Like, do they help with health outcomes would be one end goal to find out in the future. Do the symptoms people discuss, can we mine those to find interesting patterns of comorbidity? And do they match with what we see coming out of hospital data? But these are all interesting questions that we're working on currently. But just to start, we wanted to get a sense of, well, what are these communities like? What do they look like and how do they function? So we used visualization to build dashboards into the structure of these medical health communities. So for example, here's a dashboard we built for the community which discusses asthma. So I'll jump to the interactive version here. So you see a number of different charts. So along the top is a timeline, which basically shows the volume of posts over time. Below that, we have another line on which the circles represent people. They're sized by the number of posts they've made, and then the exposition encodes how long they've been members in the community. So we get a sense of who are senior members, who are newcomers, et cetera. The scatter plot on the right is log scaled and shows the relationship between initiating posts and replies to threads. So you can kind of get a sense of the amount of discussion and back and forth. Do a bunch of people come in and just ask questions and a few people answer them, or is there sustained discussion? And then below that, we have different social network views, so both a node link diagram and a matrix view, in this case sorted. And so it's useful to look at patterns in these individual charts, But oftentimes we'd like to get insight into multivariate patterns. And often it's very difficult to try and take many different dimensions and code them within a single image. And in fact, in many cases, that's a perceptually poor thing to do. You actually don't help people see patterns as well as if you break out the data into different plots. And instead, use interaction techniques to help assess the relationships between different dimensions. So in this case, for example, I can mouse over a bar in the timeline, and I can see who spoke during that time period, where are they situated in the social network, et cetera. And I might, brush along to get some sense of the dynamics of the community over time. Or I might, pick a particular person, say this senior member, and see, where do they sit within these different distributions. And I see that actually some of these newcomers are, at least currently, the more active leaders. Another thing I can see in this particular instance is that there's a lot of questions that go unanswered. So there's a lot of singletons laying out on the edge. And also, if I look at the degree distribution here, a lot of people with one link. So people who typically come in once, ask a question, leave, and never come back. So actually, just from this, we can start to learn we're looking at a community with high attrition. And by looking at the scatter plot, we actually learn that there's very few people who both post and reply. So this is an answer mill. And you see this also borne out in the matrix here, where these streaks are all the group leaders, and these are all the responses, the connections they're giving by connecting the people who come into the community and then leave. So we already get an interesting sense of the social dynamics of this community, which then might serve as some context for forming additional hypotheses and driving analysis. And just to show how this works as a point of comparison, I can look at another community, such as Lyme disease, and you see much different patterns. You still see some of that answer mill behavior. There's still many people with just kind of like one link of connectivity. You still see some of these streaks. But you also see a lot more density of connection, both in the node link and the matrix view. And if you look at the scatter plot, a much higher proportion of people who are both initiating threads and responding. And so we get a sense that this has a dual purpose. It's functioning as an answer mill to some degree, but is also a place where people are forming relationships and having extended conversations. And this might lead to subsequent hypotheses we could explore, like, is this really just a function of the people involved, or is there something specific to the conditions themselves that lead to different types of community structures? And that's something we hope to address more in future work. But what I'd like to do here with this goal is just give you a sense of how these different visualization techniques can give you insight into the data, and how, by coupled with interaction, you can start to unearth interesting patterns and start generating new hypotheses. We've also been doing some work with folks here at CHLA, and this will be talked about later in the day, so I'm just going to give you a teaser now. But what we've been looking at is, well, can we find ways to visualize patients' record data and also use that as a substrate to evaluate new analytic techniques that are being developed here at CHLA. This particular example, you're seeing a bunch of different physiological metrics. In the case, this is 8,000 different patients. I'm used to running psych experiments. And you can see the different trends. You get a lot of overplotting, so it's a bit difficult. But you do get some context in that the white line here shows a particular patient that you'd like to diagnose or prescribe treatment for. So then we might want to ask, well, what do similar patients look like? And that's some of the work that's being done here, so we can visualize the output of the similarity metric that Dave Kale and others have been developing, and then see, well, how does that compare with the rest of the data? And unfortunately, it's a little difficult to see here, but hopefully what should be read is at least a bit darker. And we can maybe get some sense of context, or we can compute statistical aggregates to compare further. So in this case, hopefully you see more clearly, we say, well, here's what the envelope of the 50 most similar patients looks like versus the rest of the patient population. And we can see, that there's good agreement along some physiological measures, but interesting differences in others, which then might help aid diagnosis or prescription. And so in this way, visualization serves not just to help us explore data, but as we develop models, we can visualize the output of those models to help verify them and further progress the research. So those are some of the examples on how visualization and analysis intertwine. I want to end by showing a number of examples of how this extends to social interaction more broadly, and what happens when we use visualizations to try and communicate results to others, and the types of follow-on analysis and discussion that can spur. And I would start off by noting this actually has quite a storied tradition. So here's a visualization that's certainly over a century old, basically a century and a half at this point, created by Florence Nightingale, the famous nurse, to show the causes of death in the Crimean War. This is a time series data showed in a somewhat exotic angular format, which caused her to name it the coxcomb, which is named after the crest of a rooster. And here what you see is that in each wedge, black is death due to other causes, red to battlefield deaths, and blue to deaths from preventable disease. And you might say, okay, well, it's interesting. And initially, this was presented in statistical tables, and Florence argued that it needed presented in this unorthodox way. The goal being to affect through the eyes what we fail to convey to the public through their word-proof ears. So she really meant this as a piece of rhetoric and argumentation to convince the reigning monarchs at the time to improve the hygienic conditions of the English army, which at this point was the leading cause of death. So here's a more contemporary example trying to achieve a somewhat similar effect. This is a map of obesity in the United States. So each circle is sized so the area is proportional to the population of the state, and the color is associated with the BMI for different people within those states. And so green is relatively healthy, and then red ranging into what is considered technically obese. Now, from this map, you'd assume things maybe aren't so bad. Most of the country's green, except for maybe Indiana, which might be in a perilous position. The unfortunate caveat is that this map is for data taken from 1995. This is 2008. Which now you can see, for example, in the Deep South, where the obesity rate's exceeding 1 person in 3. But there was also a sort of visual sleight of hand I pulled here. Did anyone notice what I did? Yeah, so the circles are bigger, and that's because the population grew. And so in this case, the color red is really, the obesity metric of interest. And so what I've done, while not incorrect in any way, was also a rhetorical device. And I think this is actually very important to realize, A, so that, as researchers and sometimes advocates, we can use visualizations more effectively, but also to raise the appropriate skepticism of how these things are used. I think they're powerful tools, but like with any media, a little bit of literacy goes a long way. So these are examples in which we might use visualizations to convey a finding or try and make a point, maybe to persuade for certain actions. But I think another interesting opportunity that, for example, the web in particular provides is the ability to get people to engage with data in a more interactive way. So if I don't like this visualization, I don't trust what you've done, I can interrogate it. I can look at alternative representations or explore the data in greater depth. And so we've done a number of experiments, both building systems and deploying them to try and test out some of these ideas. And I'll just share with you one example from our research of a system we built a couple of years ago called Sense.us, or Census, which is a web application for collaborative exploration, in this case of demographic data. So let me jump right into a demo. This particular visualization was called the Job Voyager, and it shows the makeup of the U.S. labor force over the last 150 years. And so each census decade is normalized by occupation, subdivided by gender. So in this case, blue male and red female. And we can look at this visualization. This shows the overview, maybe see some interesting trends. So for example, it might jump out to us that farmer is quite large, but has declined in recent years. So we could click that to zoom in on that pattern. And as we do so, we see that someone left a comment on this particular view. And it says, "There's no arbitrary division of labor between men and women on a farm. Unless there are millions of bachelor farmers, these numbers have more to do with the prejudices of the folks in charge of the data than with the populations of American farms." And so you can agree or disagree with a commenter, but this is the type of discussion we often saw, that this relatively small representation of females as part of the farming labor force may not be an accurate representation of the work people were doing. And so many times people commented on both potential errors in the data, they're quite good at finding that, but also potential biases in data collection, as well as, of course, just looking at observations directly within the data itself. So we might also filter by categorical variables, in this case gender, and we see some discussion, quite interesting pattern of the increased representation of women in this data post-World War II, the rise of different occupations. In this case, we see, for example, increases in cashier and clerical worker, manager, owner. And someone also noticing what seems to be a counter trend, that household workers seems to have decreased over that same period of time. And so using graphical annotations and commenting, people are actually able to begin to have analytic dialogues around this data, though admittedly in a very exploratory manner. We can also search the data through queries, right? So if I type in the letter B, I'll get all jobs that have a word that begin with the letter B. So my beauticians, barbers, bank tellers, bookkeepers, etc. But as I type, I'd like you to watch the location bar up here. Relatively small but very important design decision was that at any point I can take this URL and it's stateful. So if I put it in a Twitter or a blog post, an IM, email, someone else can come and see the exact same thing I'm looking at, thus providing a common ground for collaboration. And in particular, the one I like to share, if I continue typing, is my personal favorite view that I discovered in the system, which is, strangely, no one will admit to being a bartender in 1930. Unlike most instances that look like this, perhaps not a case of missing data. So again, human judgment is necessary to make these distinctions in many cases. And then the commenter also notes that we see more women represented after Prohibition. And we can compare that to other things, such as cook. Probably unlikely that there were no cooks in 1910 and 1880, so missing data. Or perhaps comically as well, the Great Postmaster Scourge of 1910. These being instances where people are uncovering missing data and then sharing it. And, unfortunately, a limitation of this prototype system that we use for exploration is that it doesn't have the loop back into the data that would allow people to try and correct the data and help curate it over time, which might be a useful function. So just a few more examples. Perhaps unsurprisingly, military was a favorite destination for many people who use the system. And here you see the proportional buildup of the labor force in the military as part of the Cold War. And this led to lots of commentary. One thing I would just point out here was that I reached this view by typing the query MILI. If I click this, it actually changed the query to military with a capital M. You'll notice that nothing's changed. I still get the same conversation on the right. And the insight here is that you can't join conversation to visualization views based solely on the settings of the parameters of the visualization. You actually have to have a model of the underlying state, in this case of the query result set, to create join keys that bind the commentary to the visualizations in a way where you don't end up with crosstalk, where people come to the same view but miss out on previous conversation. And then I'll show one other example. This is waiters and waitresses. And one of the reasons I like this particular visualization is because it highlights a weakness in my choice of visual representation. Remember, I admonished us all to be skeptical, both of data, but also of visual representations. And in this case, the stacked representation provides a nice view of aggregate patterns, but stacks can be biased by data values below them. So by looking at this, you might notice the really interesting rise and subsequent decrease in waitresses, but it might not have been immediately apparent that there's a really interesting pattern among males or waiters. So this is interesting. So maybe we want to add a comment to the system. So we say, why the dip in males? If we're conscientious, we can even point to what we mean. Quickly, any hypotheses? Okay, war. Sure. There was the draft during the time. Any others? Well, so some people have noticed, the large rise in women as well simultaneously, and this has had social scientists suggest to me what they termed feminization, where is the perceived gender role of the job changing over that time period as well. That might not be borne out by the subsequent increase here, but we could put this here. So we've added this comment. Maybe other people will find it. If we want to revisit it, we can create trails of views. So for example, I might go back to this view and plant a signpost. So, for example, I might say, don't miss the dip in males. And then I can take these different links and then start to link together these different visualization views so that others might discover it. So then, for example, upon arriving at this view, someone else might want to further investigate some of these hypotheses. And, for example, co-plot military and waiter, where, at least at first glance, there does seem to be an interesting correlation. And then finally, we can, of course, actually view the various comments that people have made in the system, search over that. So if we have a topic of interest, we might find out what others have done. I've been at Stanford for about 2.5 years. Still not quite so long that I might not worry about disappearing professors. So find out what this is about. And this is actually people finding schema changes as the categorization that's available within the census data has changed over the years, and people have noticed this. So maybe curtailing a more fine-grained analysis over the entire century and a half represented in the system. And so again, as I mentioned earlier, some of the things we do is not just build these systems, but evaluate them. I haven't talked in great detail about that. I will just mention that we got a number of interesting observations of how people use these types of systems. So for example, people trying to argue about, what caused military buildup. In this case, people often created timelines. This one missed a label, so someone conveniently added the label while they fleshed it out with their own pet hypotheses. My favorite examples are ones that involve what we call collaborative sense-making, where groups of people come together, make sense and generate hypotheses that an individual alone was unable to do. So in this case, there was an initial question, where did all the dentists go? There's a peak in male dentistry around 1930, and why might that be? Quite surprisingly to me, this turned out to be quite a piece of conversation. People were very actively engaged in the fate of dentists, including hypotheses such as, here's where we started adding fluoride to the water, other anecdotal stories about how often they went to the dentist as a child versus how much their kids go today. So a whole variety of both evidence and anecdotally based reasoning. But my favorite examples are ones that use data to reply to data. So for example, someone then linked to this a view that shows while dentists may have decreased, the number of medical and dental technicians has skyrocketed, suggesting there may actually be stratification within the labor force, as what was once one occupation splits into multiple occupations with different status levels. And this led people to go out and grab new data to try and verify that. So, for example, when people went and found the median salaries of dentists over the years, and this corroborated this hypothesis. And so while not formal at the level of the work of a statistician, this has been an incredibly interesting tool for generating hypotheses from data and also unearthing a number of data quality issues. And we've done subsequent research trying to understand these dynamics further, which I invite you to look at our website later if you're interested in that. But I just wanted to note that this type of interaction isn't just something that HCI, human-computer interaction researchers are exploring in the laboratory. It's happening actively now, including in the health domain. And so one site that I've been very interested in for the last couple of years is Patients Like Me, where people come in and they join communities around chronic illnesses and share their data. So both their vital signs and often their treatment regimens and outcomes, sometimes just to provide support and to learn. But interestingly enough, also to organize in very interesting and perhaps non-obvious ways. So, for example, there was a journal article that came out that said that lithium may have beneficial effects for people suffering from ALS. And this was shared on Patients Like Me and got a number of people on the site quite interested. So they self-elected to go on lithium regimes, which is probably the scariest thing a doctor can hear. But interesting enough, but these were people who had a chronic illness and they were also desperate, and this was their choice. But perhaps wisely, the folks in charge of the site noticed this as well and then collaborated with the patients and even were able to stratify them into meaningful samples, run a clinical study with the users of this site, and then has since published a journal article showing that, in fact, the results of the Italian researchers that showed benefits of lithium, they were not able to find with a sample size 10 times larger than that. And so there are interesting things that these technologies, so combining social interaction and the ability to access and manipulate data more effectively, can enable. And I really believe and hope that we've only scratched the surface in those regards. And so to wrap up, I just wanted to reiterate that data analysis is a wild and woolly process, and that throughout these different stages and these cycles of iteration, there are many opportunities in which interactive or visual techniques might help improve our abilities. And this is in no way sort of in contrast to statistical modeling or other analytic techniques, but rather it's the search of finding the ways in which these different methods best resonate together to improve outcomes. And so my parting thoughts then were just, again, analysis is often iterative and exploratory, and visualizations can help us form hypotheses and can also aid in the interpretation and verification of analytic results. And I think that provides an interesting challenge for designers and system builders, that how do we enable tighter iterations? So a lot of times this visual data analysis is within the inner loop of our research process. So as we're initially exploring data, as we're verifying models, we want this process to be quite quick. And in fact, in many cases, it would be ideal if we could generate and specify models in an interactive manner to speed up that loop even further. And we can do this, one, through the use of appropriate representations, such as visualizations, to enable rapid perception of the patterns of interest to us. And then also interaction techniques that allow us to rapidly transform, manipulate data, and create the visualization views that are responsive to our questions. And the final goal is to hope that we can create these interfaces, coupling with large data infrastructures that will allow us to do this at the pace that's resonant with the speed of our thought. So the idea, hopefully, is that as we can formulate questions, we can at least begin, even if approximately, to get answers from the data resources that we're creating. So thank you for your time, and I'm happy to take any questions.